Whenever we open a new window on the universe, we discover something new, whether it's figuring out how to see to greater distances, like with telescopes, or down to smaller size scales, like with microscopes, or perhaps expanding our vision to new wavelengths of light, or via exotic means, such as in neutrinos or gravitational waves. Well, the 2023 Nobel Prize in Physics has been awarded to 3 physicists for opening just such a new window, but it's not a window to a new size scale or a new mode of seeing, it's for a new window in time. It's for attosecond physics, the billionth of a second that represents the timescales of the insides of the atom. This year's Nobel in Physics is for a microscope in time. Every 230 million years, the solar system completes one orbit around the Milky Way. Every 243 years, Venus passes between the Sun and the Earth. Every year, monarch butterflies migrate between the United States and Mexico. Every 3 seconds, a kinesin protein travels down one of your cytoskeletal filaments. As we look to smaller and smaller scales, we find faster and faster processes. Makes intuitive sense. Big things surely have a hard time moving faster than their constituents. The trend continues to the smaller scales, the motion of individual atoms during chemical reactions, or of individual electrons moving in atoms. The timescale of their motion is not measured in microseconds nor nanoseconds. They're measured in attoseconds, and this is a very small amount of time indeed. There are as many attoseconds in a second as there are seconds in the entire history of the universe. Probably there are things to be discovered buried in that universe of phenomena that play out every single second. And this is why the Swedish Academy of Sciences made a very reasonable choice in awarding Anne Lehoulière, Pierre Agostini, and Ferenc Krauss the 2023 Nobel Prize in Physics for bringing into existence the field of attosecond physics. Before we get to how our newly minted laureates managed this, let's talk about why it was so difficult in the first place. Think about what it takes to observe something. Observing means watching things bounce off other things, whether it's light bouncing off an apple into our eyes or electrons bouncing off a tardigrade into an electron microscope. The smaller the object you want to observe, the smaller the particle you need to fling at it. For example, you could get a rough idea of my shape by hurling beach balls at me and seeing how they scattered, but you'd get a better picture pelting me with ping pong balls, or even better, photons. Resolving small distances requires scattering many particles with small spatial separation, each with a well-defined spatial location. Resolving very small times requires scattering many particles with small separations in time and with well-defined temporal locations. Imagine you want to take a video of a fast process, say a hovering hummingbird. If your camera aperture stays open too long, you'll only capture a blur over the span of its wing's motion. The aperture opening needs to have a well-defined temporal location. In other words, it needs to be quick. But quick exposures aren't going to give you a very good movie of the hummingbird if they aren't separated by less than a wing beat. You'll only get a random seeming collection of stills. You need short temporal separation if you want a meaningful sequence. So how do you get a tight temporal location and short temporal separation down to the attosecond? Let's start by thinking about the temporal location of a photon. That's limited by its period. You can't clock a photon to any time smaller than a single up-down cycle of its electromagnetic wave. Light with a period of attoseconds is in the X-ray part of the electromagnetic spectrum. We routinely use X-rays in imaging, so we should be fine there, right? Well, not quite. A typical laser fires one photon every few femtoseconds, and that's 1,000 times longer than an attosecond. So even if you make a movie of attosecond motion with a conventional laser, the abysmal frame rate would turn that motion into a hopeless blur. It is possible to build an extremely fast laser, for example, free electron lasers. They require an electron accelerator to work, and they are honestly too powerful and way too dangerous to give to the average physicist to play around with. And besides, blasting your sample with an X-ray laser of the power required would be like taking an X-ray using a nuclear explosion. It's just not practical. So, enter our first Nobel laureate. Back in the 1980s, Anne Lehoulière and her colleagues were playing around with irradiating argon gas with infrared lasers. They observed something pretty weird. Normally, when you irradiate a gas, you'll get different types of light out. That includes some of the light you put in, some light corresponding to electron transitions of the atom, as well as some random thermal light from the jiggling of the atoms. But Lehoullier's team noticed that the outgoing beam consisted of the original ingoing frequency plus some higher frequencies that didn't correspond to any known process. So where did these other frequencies come from? Well, it's pretty cool. As a laser pulse passes by a gas atom, it can nudge the electromagnetic field holding the electrons in place in such a way that the electron can escape by quantum tunneling. The electron can then be pulled straight back to its atom, and it will release the energy it gained in a single photon. Think of it like stretching a spring and letting it go. That one photon will have a higher energy than each of the many photons that made up the laser pulse. In fact, it'll have a frequency that's some integer multiple of the laser photons. And a cool detail is that it'll be an odd multiple of the frequency for complex reasons regarding symmetry. This process is called high harmonic generation, and it basically adds overtones to the laser beam. Play a note on any musical instrument and you'll get the fundamental frequency plus higher frequency overtones. The fundamental corresponds to the longest wavelength standing wave that you can fit along a resonating string or air column, while the overtones correspond to all shorter wavelength standing waves that also fit. The balance of the strength of the overtones determines the precise character of the sound of that instrument, its timbre. So, the timbre of a laser was altered by an argon cloud. That's a cute effect, but not quite Nobel-level science just yet. To get to attosecond physics, we need one more analogy with acoustics. Listen to this. It's a very low G note, and this is a very low A. Individually, there's nothing unusual, but if we play them together, we hear a sort of wah 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 wah. This is known as a beat in acoustics, and it's due to the fact that the sine waves of the G and the A line up perfectly at certain points, making them louder with constructive interference, while they're perfectly out of alignment elsewhere, so cancel out with destructive interference. For a pair of waves, the beats are quite spread out, with a lower frequency than both of its parents. But if you add more and more waves, it's possible to narrow the width of the beats, so you end up with sharp pulses with very little in between. For that, you need a large number of frequencies of similar intensity. For example, the rich spectrum of overtones produced in Anne Lehoulier's experiment. In fact, it proved possible to get pulses that were mere hundreds of attoseconds in their temporal width. Our new attosecond resolved pulses weren't ready for application just yet. The potential value is that they would allow us to measure attosecond scale events. But if the pulses themselves are attosecond scale events, how can we calibrate them to start with? It's like trying to measure your height with a series of rulers whose individual length you don't know. And here we get to our second Nobel laureate, Pierre Agostini. Agostini was able to calibrate the pulse train by again using constructive and destructive interference, this time in reference to the ingoing laser beam. He did this by deflecting part of the beam and adding a delay before recombining it with the now frequency multiplied beam. In this way he could measure the width of pulses, clocking them at 250 attoseconds. He also found that the pulses were what we call phase locked, which means the beats were nice and consistent and just what we needed for attosecond measurements. These pulse trains provided pulses with attosecond temporal locality and separation, just as we required. But for some applications, it would be preferable to have a single isolated attosecond pulse. And that effort is thanks to our third laureate, Ferenc Krauss. I won't go into the gory details, but for your viewing pleasure, here's the Rube Goldberg experimental setup. With intricate phase and amplitude manipulation, they were able to create isolated pulses of 650 attoseconds, whose width was known to 150 attosecond precision. Okay, attosecond resolution achieved. So what do we do with it? As Krauss himself states in an interview, they invented this technology because looking at nature in a new way is wonderful. Literally, it fills you with wonder. But we just did give ourselves a new superpower, so it'd be a shame not to use it. The first application of attosecond pulses was to look at electron motion in atoms and molecules. Electrons travel the breadth of their orbitals in a handful of attoseconds, or rather, the fuzzy quantum clouds that define the electron in an atom change on that timescale. By hitting these clouds with attosecond pulses, we can study the shapes and dynamics of these electrons. Attosecond pulses can also be used to manipulate electrons on tiny timescales, which has a number of powerful applications. One effort that Ferenc Krause's team is working on at the Max Planck Institute for Quantum Optics is in molecular fingerprinting, in which attosecond pulses are frequency-tuned to cause vibrations in specific molecules. In this way, the detailed molecular composition of a sample can be potentially catalogued. The Krause team are using this to develop molecular fingerprinting devices for medical diagnosis. Another very exciting possibility is the creation of ultrafast electronics. If we have two metal plates with opposite electric charge, and we shoot an isolated attosecond pulse at one of them, it can be absorbed by an electron which hops to the second plate. This is the photoelectric effect, and we've known about it for 120 years. But in the configuration I described, it's also a transistor, a key component of most of our technology. Regular transistors control the flow of electricity between two charged plates by changing the charge in a third plate. But this new type of transistor controls the flow using light itself, which can in principle be much, much faster, especially if the pulse width is measured in attoseconds. Krause claims that it may be possible to increase the power of computers by a factor of 100,000 this way. And that sounds optimistic, but even if we get a fraction of that, it's an incredible achievement, and we may save Moore's law for a few more decades. Those are just a couple of applications in medicine and electronics, but as we look at the universe with this new tool, we are bound to find new applications and to make new discoveries. After all, every time we open a new window to the universe, new mysteries are revealed, whether that window is to the largest, the smallest, and now the fastest phenomena in space-time.